Example 3, a radioactive sample of radium-225 has a half-life of 15 days. The mass in grams of radium-225 remaining over time in 15-day intervals can be modeled using the exponential graph. So our graph's drawn for us here. A, what is the initial mass of radium-225 in the sample? What value does the mass of radium-225 remaining approach as time passes? So our initial mass would be at time 0, so it's 1.0 grams. What value does the mass of radium-225 remaining approach as time passes? As time passes, it's approaching 0 grams. It's approaching here. So it approaches 0 grams as time goes on. So as time increases. B, what are the domain and range of this function? So if we take a look at the domains, you're looking, we usually consider it the x values. In this case, it's not the x variable. We're using a t for time. So for the domain, we're gonna say t such that. So we choose our variable and it's everything to the right. There's no arrowhead here, so there's an endpoint. It includes 1. So, it includes not 1, sorry, the y-intercept's 1. It includes 0 and continues to the right. So t is greater than or equal to 0, where t is still the element of real numbers. Okay, this curve is connected. We can have, points in between these 15-day intervals. The range, the variable for range we're going to use is m rather than y. So we're saying m such that, and it's going from 0 does not include 0 as that's an asymptote, and it up to 1 where it includes 1. So 0 is less than 1, less than or equal to 0 is less than m rather, is less than or equal to 1, where m is the element of real numbers. Again, there's all points, all real numbers are included, fractions, decimals, etc. Let's look at C. Write the exponential decay model. We're talking about the equation here that relates the mass of radium-225 remaining to time in a 15-day interval. So we can use the strategy of when we look at the point 1 is plotted, the y value is 1/2. So at t equals 1, m is equal to 0.5. So that means that that's going to be our base number. So to write it as a function, we're going to say m of t. I'm going to use a fraction, 1/2 t. Now, it's important to note that any kind of half-life question will always have a base number equal to 1/2. So we can kind of count on that being true. Then D, estimate how many days it would take for radium-225 to decay to 1/30th of its original mass. So this is going to be your mass. We're going to plug that into our equation for m of t. And we're going to solve for t. Now, we haven't learned logarithms yet, so that's why this question says estimate. So we're just going to do an estimation until we learn how we could do this one algebraically. So we want to choose, think of exponents. 2 to what exponent is going to get me close to 30? So 1 to the 2 over 4, for example, is 1/16. 1 over 2 to the 5 is equal to 1 over 32. So that means it's quite close to the 32 compared to the 16. So we would say that t, this again is our estimate. So it's our estimation here. T is approximately 4.8 or 4.9. Okay, I'm gonna probably go with 4.9 here. You can check in your calculator. You know it's between 4 and 5, right? It's closer to this one, so that's where I'm coming up to with the 4.9. Now that's the time. These are 15-day intervals, so therefore we would take 4.9 times 15, and it's approximately 73.5 days. If depending on numbers, sometimes you can estimate on the graph, but we would not be able to easily locate 1 over 30 on our y-axis. You can also check your answer using a calculator and compare if you plug in, 1/2 to the 4.9, is it close to what 1 over 30 is?